Let's continue our discussion on the dependence of number of states on the external parameters. So if you remember, we have found out that the number of accessible states for energies in the range E to E plus delta E depends on the value of external parameters as well. For example, in the case of ideal gas in a three-dimensional box, we said it's the volume. And the energy levels themselves will shift with changes in the external parameters such as volume. And the amount of shift in the energy level due to a change in the external parameter x we have defined to be x sub r for the response of the art state to energy to the change in the external parameter, and we have shown that x sub r depends on what state we talk about, so it's a function of the values of the quantum numbers. Now we're going to subdivide x sub r into small intervals delta x such that the variation in x sub r is small enough that the corresponding variation in the number of accessible states omega ex is negligible. So you can see how I'm subdividing x sub r into delta x intervals, and you can see that for the value of x sub r, xi, so the ith value xi, and this value will be then xi plus delta x. So in this range I have a constant number of accessible states omega I. So delta x is small enough that the change in the number of corresponding change in the number of accessible states is negligible. So the number of omega I of those states for which we have xr has a value in the interval between xi and xi plus delta x. If we sum over all such omega I values over all these possible intervals, we will get the total number of accessible states for energies in the range E to E plus delta E when the external parameter has a value x. So basically we're looking at a subset of a number of accessible states such that in this subset omega I, xr has a value in the range xi to xi plus delta x. Okay, so if x sub r has a value in the range, a specific value xi to xi plus delta x, the corresponding number of states, which is a subset in the number of accessible states, will be omega I of Ex, such that in this subset of accessible states, the energy of each state varies as by the same amount xi dx, because delta x is very small. So this is when x changes, the external parameter changes by an amount dx. So we're going to have change in the energy level, dE is xi dx. So if we have del del x value x sub I positive, then the change in the energy, the shift in the energy levels will be positive for all particular states omega I with xr in the range xi to xi plus delta x. Okay, so the states that are in this interval, energy interval xi dx, will be shifting upward if xi has a positive value. So we will find that energies of such states will change by the same amount dE, which is xi dx. So energies of such states, those particular set of states that has a value xi, that have a value xi, will change by the same amount dE. So remember that we have a different xr value for a different state. So basically we're grouping the states that are close enough and that will have a particular variation with the changes in the external parameter, so that xr has a value xi to xi plus delta x, where delta x is small, such that the number of states we're talking about whose response is given by xi is pretty much a constant. So the number of accessible states, particular subset of accessible states that will respond by xi will be the same in this interval xi to xi plus delta x, and they will be responding by changing the energies of such states by an amount dE, where dE is equal to xi dx. xi is del del x value, particular value, and dx is the change in the external parameter. And we have how many states per energy? So there are this subset of omega I states divided by delta E states per energy, and we're going to have the density of states omega I divided by delta E multiplied by dE, the total number of states will be omega I divided by delta E multiplied by xi dx states in the energy range xi dx. So that will be the number of states that is in this range. Now I call, or I define gamma I as a function of energy those states the number of states among the omega I states where xr has a value between xi to xi plus delta x, energy e to e plus delta e, and x is changing by an amount dx. These states of the ith subset of accessible states and I'm looking at a subset of this states whose energy is changed from a value less than E to a value greater than E. So basically these are the fresh states that have entered this range. When the external parameter is changed from x to x plus dx. So these particular number of states that are entering this range will be equal to the number of states per energy, omega I, divided by delta E multiplied by dE. So these are the states that are shifting up in energy by xi dx, and they are entering this range e to e plus delta E. So where I have the omega I number of accessible states. So you can see that this is E, and then here I have the level or the width of this range is given by delta E, and you can see that there are some states that are below the level E by an amount xi dx, which is my dE. They're all shifting by an amount xi dx and entering this range, and of course there will be some of them that are leaving this range as well by the same amount xi dx. So we have the freshly created levels within this range, or the levels that have shifted to this range. It's the number of accessible states of this that have this response xi to changes in the external parameter per energy delta E multiplied by, so it's like the density of states multiplied by the change in the energy dE xi dx, which is the amount of shift in these energy levels. So you can think of this as a rho I, density of states, multiplied by dE. So basically what we find is that if an energy level is below E and it is residing in the range xi dx, it will move above E to enter this range of interest. Okay, so I call omega Ex once again is the total number of accessible states with energy between E to E plus delta E when the external parameter has a value x. So this is the total number of accessible states. Now I'm going to call gamma E is the total number of states, not just the states that have a response of x value xi, del er del x is xi. I'm talking about total number of states among all possible accessible states of the system whose energy is changed from a value less than E to a value greater than E. So I'm talking about all states that have shifted to have their energy levels lie above E when the external parameter is changed from a value from x to x plus dx. So basically, in order to find the total number of states that are shifting, I have to look at all ith subsets for gamma I e, where I have among the omega I states of the ith subset whose energy changes from a value less than E to a value greater than E. So I have to count all possible i's. So basically this is going to let me, this I index will go through all possible xr values. So for all of the possible xr values, I will be looking at the shifts in all the states, and this will give me, because I'm particularly interested in the ones that are moving above an energy E, this will be equal to sum over I, the number of states whose response to changes in x is that lies in the range xi to xi plus delta x, that is multiplied by xi, and because this is going to be in the summation, then basically I'm isolating dx divided by delta E. So for gamma I have substituted this expression. It's the number of states per energy, omega I divided by delta E, whose response is xi multiplied by xi dx dE. So it's the number of states that is entering this region. And now I'm calculating the contribution from all xr values. So I'm going through all I index values, and omega I ex xi dx del E. So del omega I divided by del E was the number of states per energy, multiplied by xi dx was dE. So remember, so this is from gamma I. Also let me remind myself here, xi dx divided by delta E is basically dE divided by delta E. So I goes over all XR values. So it's the index for going over all XR values, so that I will find for gamma E, if I multiply both sides of this equation with the number of accessible states, total number of accessible states, sum over I omega I EX divided by total number of accessible states EX. So I multiply and divide by a total number of accessible states, XI dx divided by delta E. I realize that due to my postulate of equal a priori probabilities, omega I divided by omega is basically giving me the probability of having a value x sub I for R. So this is basically a probability that x sub R is equal to xi. That's by definition and from equal a priori probabilities postulate. So basically I see that this total number of states who are entering this or going above energy level E is omega EX. Then I have the summation over the probabilities, the summation of Pi xi. So let's call this Pi. And then I have dx divided by delta E. If you multiply the value of a variable with its probability and go over all possible values, then that is by definition the mean value of x. So we find that the total number of states that are entering this region is number of accessible states, total number of accessible states divided by delta E multiplied by mean value x bar dx. So basically this looks like rho, and this is the change in the mean energy of the system. All right. So x bar is the mean value of xr over all states R in the interval energy interval E to E plus delta E, and this comes from equal a priori probabilities at equilibrium. So this is our postulate. Now this x bar dx will be del er bar del x dx is the work done on the system, d bar w, and dE bar is equal to d bar w for an adiabatic process. So basically I'm assuming that the only thing that is changing in the system is this external parameter. There is no change in the energy of the system due to heat exchange. So x bar dx gives me dE bar for an adiabatic process. We're going to continue discussing how the number of accessible states will change when x changes by dx in the next video by looking at the number of states that are entering the interval e to e plus delta e and leaving this interval. So just to sum up here what we have done, we have looked at xr, which is the change in the energy levels with the external parameter x, particular value in a range xi to xi plus delta x. So all possible values of xr we have divided into intervals of delta x, and this is done such that the corresponding variation in the total number of accessible states is negligible. So if xr has a value in the range xi to xi plus delta x, there is a corresponding number of accessible states, subset of accessible states, omega I of ex, such that the energy of each state varies by the same amount xi dx when x changes by an amount dx, and the number of accessible states omega I is basically the same for xi to xi plus delta x values. So they're all shifting by the same amount. So if xi is positive, the shift will be positive, and we're going to see the energy levels going up. Now, those states whose energies will be energy levels will be shifting up by xi dx divided by the delta E, the energy interval delta E, we find the number of states per energy that are behaving in this manner, and when we multiply it by dE, we get the number of states in the range xi dx. So those states that are moving up and so that their energies will be greater than E, we show by gamma I of E, so that gamma I of E is the number of states per energy, omega I divided by delta E, multiplied by the change in the energy, dE. So this is basically saying that if you have an energy level that is below E and it is in the range xi dx, because all energy levels will shift by the same amount, it will move above E so that it will be entering my energy range of interest, e to e plus delta E. So if I call total number of accessible states in this range e to e plus delta E when the external parameter has a value x, and gamma E is the total number of states among all of such states whose energy is changed from a value less than E to a value greater than E when the external parameter is changed from x to x plus dx, then I have to sum over all x capital X values, x sub x I values. So I goes from the initial value to the maximum possible value, so that I will be covering all xr values. So gamma E is basically summation over I gamma I of E. So number of accessible states of the behavior whose shift is by amount xi dx divided by delta E, that the density of states for this particular type, multiplied by xi dx, the change in the energy. Because the I index summation affects only omega I and xi, I have grouped them together, and I have multiplied the top and bottom with the number of accessible states, total number of accessible states, for E energies e to e plus delta E when the external parameter has a value x, and I find that I'm looking at the probability of having xr a value xi. So probability multiplied by the value summed over all possible values gives me the mean value. So the number of accessible states multiplied total number of accessible states multiplied by x bar dx divided by delta E is what I'm getting. So the total number of states that are moving up to enter this region E to E plus delta E is the number of accessible states omega divided by delta E, that's the density of states, multiplied by x bar dx, and x bar dx will be equal to dE bar when the process is adiabatic. So x bar dx is del ER bar del x dx, and the change in the energy levels will be due to the work done on the system d bar w for the adiabatic process. So we're going to use this omega E in order to finally calculate or reach our change in the total number of accessible states when x changes by an amount dx in our next